Good morning. Woo. How about you guys? It's a beautiful Tuesday. All my windows are open. Everything outside feels nice, and I cannot wait to go outside after this because, quite frankly, my room is getting stuffy. All right. So today we're going to talk about the last piece of section 5.3. 5.3 dealt with polynomials and specifically how to do things like determine the multiplicity, determine the intercepts, using the end behavior, and of course the IVT. The big thing about today is we're going to be looking at specifically how to graph these things. Now, to graph these, it's important to note the big things. First of all, when we're graphing these, you're always going to get an approximate solution. So when you graph these, the answer is never going to be perfect. The goal is not perfect. If I wanted perfect, I'd tell you to graph these on Desmos or graph these with a graphing calculator, because then they'd be perfect. The goal is to see how you can infer information and learn from what it is you see and fit different pieces of these sections together to figure out what a graph of these should look like. Now, that does not mean that our graphs are going to be wrong or that there's no wrong answers. There are things that are clearly supposed to be one way versus the other, and they're all going to fit together into one specific problem when we put them in that form. So let's take a look at how to graph some of these problems, and I'm going to do it by looking at all the even problems we have in the textbook, so you can get a real sense of what these problems feel like, and still have the problems in the textbook in the previous section to see through their steps, so you can kind of see where they fit. Now, when looking at these kinds of problems, one of the big things to note is this process. So, my process for how to use what we are given to graph. The first couple steps are all kind of weird. My first step is I want to determine positive versus negative. Now I say it's my first step, but I can really do this in any order. I just think it's an easy one to start with. And same with part B. Like, you can do any of these in pretty much any order and eventually get the solution. It's just I like going in this order because I think these start off with the easy ones first, and that makes my life a lot better. Okay, so is it positive or negative? And then what's the degree? We talked before about the degree of a function. The degree of the function, remember, is the highest powered variable. And so if you have like an x cubed and it's the biggest one, then the degree would be 3. If you have an x to the 5th power and it's the biggest one, then it would be a power of 5, or a degree of 5. The coefficient, the number in front, doesn't matter here. What matters is what the actual power is. So sometimes I'll use this word and I'll say the power of the function. They mean the same thing. It's more accurate to say the degree because it's the correct term, but power usually gets the same information across. Okay, third thing. I want to find intercepts. We talked about that last time about how to find intercepts. And then part D, I want to find multiplicity. And the last thing is end behavior. So with these few basic steps, I'm going to try to solve every single one of these problems and graph them. And if I don't need to graph them, I can always work backwards to figure out other pieces of information using these same basic things. So let's take a look at our first problem, which is number 42. Like I said, for your homework up there, I'm going to be doing all the even ones to kind of get you a good idea of what these feel like. So let's take a look now at number 42. Okay, and in the little side areas here, I'm going to be listing out some of these things just so you know where they came from. Part A, I want to determine positivity or negativity. Is it a positive function or negative function? Now, you can determine this by looking at just the x parts of the terms and multiplying them together. So if you're looking at 42 over here, I see that I have, and I'll zoom in a little bit to make it a little easier to see for everybody. I have x plus 3 squared, x minus 2. So this tells me I would have x twice, so x squared times another x. This tells me I'm going to end up with x times x times x, or x cubed, which is a positive answer. Notice I'm only concerning myself with which pieces are belonging to the x's. If I compare this to 43, it would also be a positive answer. X times another x would be x cubed, and so again, it's just a basic function. Now, next piece I want to determine is the degree, and I actually already found it. It's a degree 3. How do I do that? Well, I just add all the powers together. So I take the power of 2 that's here, plus the power of 1 that's hidden here, for a total of a power of 3. What this tells me is this is going to match based upon every cubic function that is positive. So I'm actually going to pull up my notes here. This is a really important piece to help with this. This is from section 2, which was last week. Because I already talked about n behavior before, look at how this fits up. Like, I know it's positive. I know that the power is a 3, so I know it's odd, so I know it's going to look something like this. Maybe not perfectly like this, but something like it. And so I can use information to help guide me. So part A, I determined it was a positive function. Part B, I determined I had a power of 3. Next thing I need to do is find the intercepts. Okay? Well, this is usually the longer one, but with many of the functions you have today, it's actually pretty easy. So the x-intercepts and the y-intercepts are different things. Let's start with the x-intercepts. To find the x-intercepts, I need to use a property of mathematics, the fundamental theorem of algebra, which allows me to take these 3 pieces, yes, that's 3, 2 here and 1 here, and solve them separately. When I do, I get a negative 3 and a positive 2 for my x-intercepts. So a negative 3 and a positive 2. That comes from, in this function, if I solve this first piece, I would get x plus 3 equals 0. Subtract 3 from both sides to get x equals negative 3. We take the second piece, set equal to 0, and this is all reviewed from last time. Remember, last time was about finding intercepts. We take each piece, set it equal to 0, and solve. Negative 3, positive 2, done. To find the y-intercept, what I do is I plug in 0 for x, so 0 plus 3, and then 0 minus 2. 0 plus 3 is 3. Square that is 9. 0 minus 2 is 2, negative 2. And negative 2 times 9 is negative 18. So already I've got a lot of information here. I know it's a positive function with a power of 3. I know that I have intercepts at negative 3 and at positive 2. I know it has a y-intercept at negative 18. Okay. Part D. I want to determine any multiplicities. And then finally, part E, I want to determine any end behavior. So, let's talk about multiplicities. D. Multiplicity. Well, 3 has a multiplicity of 2. Sorry, negative 3 has a multiplicity of 2. And 2 has a multiplicity of 1. Now, in a second, I'm going to show you how to graph that piece. And then finally, the end behavior we'll do afterwards. Okay, so ready? Step 1. The first thing I'm going to graph, so this will be added to my notes. When I'm actually asked to graph it, I want to find these 5 things eventually. But when I graph it, I want to graph intercepts first. I want to make sure there's 100% right. Then I want to graph end behavior. Then I want to graph multiplicity. And you notice that I've skipped out on degree. Well, degree helps me graph end behavior. Notice I skipped out on positive and negative. Well, positive and negative helps me graph end behavior. And so let's take a look at this function. I'm going to graph it in this order. I'm going to graph the intercepts first. Then I'm going to graph its end behavior. Then I'm going to graph its multiplicity using all the information I have found. So step 1, let's do the intercepts. To make this a little easier, I'm actually going to count by 2's. So this is going to be at 2, 4, 6, 8, 10. This would be 2, 4, 6, 8, 10. This would be at negative 2. You get the idea. At this point, I'm just rambling. I'm going to stop when I know I'm at a point where I can actually graph this thing. So I get negative 16, and then negative 18, and then negative 2, and negative 4. Okay. So this looks good. All right. So step 1, we'll do mine in purple. My x-intercepts are at negative 3, which is right there, and positive 2, which is right there. So I put my intercepts down. I'm going to wait to label these at the end, but I am going to check mark them to remind myself that I've done that piece. Okay? My y-intercept is at negative 18, which is down here. There we go. So I got 3 dots so far. 1, 2, 3. Now the question is, what else is going to happen? Well, I know from my list, the next thing I should think about is end behavior. So let's go to end behavior. We have a function with a degree of 3, and it is positive. If I look at my function, degree of 3 is odd, and it's positive, so it's going to look something like this, meaning the left-hand side of it is going to go down over time. The right-hand side is going to go up over time. So I know out over here, somewhere, it's going up, and down here, or as we go farther to the left, it is going to go down. So the question is, which one's which, and how do we get that to work? So let's go to the next piece. So notice I've left a big gap here in the middle because I'm not sure it's happening in the middle. But I do know as we go left, eventually it's going to go down. As we go right, it's eventually going to go up. Let's talk about the last piece. So the last piece you want to look at is multiplicity. Multiplicity is going to fill in all these middle parts. So what multiplicity does is if the multiplicity is even, we are going to bounce. If multiplicity is odd, we're going to cut. What on earth does that mean? Well, take a look. Negative 3 has an even multiplicity. It's multiplicity 2. What that means is this line is going to come up here. It's going to touch negative 3 and then bounce back. Meaning it's going to come backwards. We know it's going to come backwards at least as far down as this intercept because it has to go through this next dot. So really we're playing a game of connect the dots. We have this side, we hit here, it bounces off the negative 3 because it has a multiplicity of 2, and then it starts to come back. Now, when it gets the 2, well, 2 has a multiplicity of 1. Odd multiplicities cut through. So what that means is it's not going to bounce at 2, it's going to cut through 2. Like that. Leaving us with this kind of wonky looking function. So, it's not perfect, right? But you'll notice it does have a kind of similar theme to this one, right? The left-hand side goes down over time, the right-hand side goes up over time. It's just in the middle, there's some wonkiness to it. Now, to illustrate just how good this process is, allow me to show you what this function looks like in its actual form. So I'm going to pull up Desmos on my computer. There we go. In Desmos, I have the function x plus 3 squared x minus 2. If we zoom out, yeah, I mean, let's compare that side by side. Like, it ain't perfect, but it's definitely doing what it says. It is going up as we go farther to the right. It is going down as we go farther to the left. It does bounce off of negative 3, and it does cut through positive 2, and it does dip down all the way to the 18. That's pretty neat. Like, this is a fine interpretation of this function. Not perfect. Never perfect. But the goal is to be a good approximation for what this thing looks like. And notice how we did it. We just investigated all these little components. We investigated its positivity or negativity and its degree, because that helps determine things like end behavior. We investigated its intercepts, because we can graph those intercepts. We investigated its multiplicity, because those multiplicity is going to tell me how it's going to interact. If it's even multiplicities, it's going to bounce, as we call it. Bouncing is where you hit the intercept, but then come back. And you can do it either way. So a bounce, in this case, let's put a little picture next to these notes. So a bounce is when you have your graph, and you hit it and you bounce. Or if you have a graph, you hit it and you bounce. Okay? It's going to hit the intercept and then bounce off the axis. Whereas a cut, if a line, a cut's going to go through it. Now I can go through it in any way it needs to in order to make the graph work, but a cut's going to go through it. So, using that information, the goal is to get a fairly accurate representation of what this graph looks like. And this is an accurate representation of the graph for 42. If not perfect, at least decent. And so that's it. This is how we approach a lot of the problems we have tonight when it comes to the graphing part of it. We're not interested in an accurate picture. We're interested in using the information we have to get a good picture. Now, do not just graph these and copy them. It becomes painfully obvious when somebody does that because, quite frankly, you end up with too perfect a graph. It's very obvious. Okay? Do not do that. Okay? I cannot stress it enough. On your test, I'm not going to focus on these as much because it is so easy to cheat that way. There may be only going to be one of these, but there is going to be a significant number where you have to go in reverse, like these ones down here that we're going to talk about. And you have to know your stuff to do 48 compared to 42. 42, you can just cheat by graphing. But 48, if you don't know your stuff, you're never going to get it. So let's look at now at 44 and go through the same process. Like I said, you can do these steps in pretty much any order. Eventually you're going to find them all. Just make sure you do find them because it does help to graph them, as you saw just a moment ago. Let's start with the first piece. A. I want to determine if this is positive or negative. Well, what I do is I look at the coefficients and the powers, and I multiply together. This tells me there are 3 x's here and 2 x's here for a total of 5 x's. So I know it would have a degree of 5. And because none of them are negative, I know it's going to be a positive solution. Okay? Next. C. Intercepts. Well, part 1. If I plug in, I should get from this one, positive 1 for my x, and negative 3 for my x. For the y, I plug in 0. When I plug in 0, make sure I don't confuse that with positive and negative. Okay, so 1 and negative 3. With my y, I would end up with, okay, plug in 0, so 0 minus 1 is negative 1. Negative 1 to the 3rd power is negative 1. Plug in 0 here, 0 plus 3 is 3, 3 squared is 9. So I end up with negative 9 as my y-intercept. So, got positive 1 and negative 3, got negative 9 for my y, and if I want to, I can now immediately go into graphing this thing. Now, I'm going to do these by ones, so it's going to be 1, 2, 3, 4, 5, 6, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9. Okay, so I have positive 1, that's one of my answers, on the x-axis, and negative 3, so 1, 2, 3, there it is. And I have negative 9, which is down here. So already we're looking pretty decent, okay? Now, let's go to the next piece. D, multiplicity. So when I talk about multiplicity, my 1 has a multiplicity of 3, which you'll notice is odd. That's really important. My negative 3 has a multiplicity of 2. That's pretty important as well, because it tells me how it's going to act. Is it going to bounce, or is it going to cut? Well, let's do it. So I've done the intercepts. Now I do end behavior. According to my function, I have a power of 5 and it's positive, or a degree of 5 and positive. Odd, positive, this top one, which again down and to the left, up and to the right. So down and to the left, up and to the right. There we go. Okay. Now, I know eventually I'm going to connect all of these dots together. So I'm going to connect this up to here, down to here, and up to here. Now the question is, do I go up and through, or do I bounce? When I come back, do I go through? Do I come here? Do I bounce? Or do I just go straight through? There's so many questions to answer. That's why having these little components over here helps me. So, the 1, it has a degree of 3. 3 is odd. Since it is odd, that means, according to my little graph here, it's going to cut. So, it's going to cut through the 1, like so. The negative 3 has a multiplicity of 2. 2 means it's going to bounce. So, it's going to come from the bottom up to negative 3, and then it's going to bounce off of negative 3 and start heading back down. So now I can kind of see that it's definitely going to follow this path. It's going to kind of come over here. It's going to probably come over this way. And come on up. That is a decent graph. Is it perfect? No. And here's the thing. I'm kind of forcing this to be the bottom, but it could be just as likely that it goes farther down. All I know is this is an intercept. And so I'm just trying to connect these 3 dots using the end behavior and all the little context clues they have given me. And again, if I was to graph this function, I get a pretty decent looking solution. Again, not perfect, but better than nothing. So people always ask, how do people graph things before we had the advent of things like graphing calculators? This is how. So we had x plus 1 to the 3rd power times x, I think I got it backwards. Excuse me. So look at that. Notice a cool thing happens right here, which is really important. Okay? Look at what happens at 1. Right here at 1, notice what it looks like. It looks like a cubic function. So what the multiplicity will tell you is not just whether it's a bounce or a cut, but what kind of function it looks like. So to answer this part, let's remind ourselves of some things. What does a 1 power look like? 1 looks like a cut. What does a 2 look like? 2 looks like a parabola. So what we call a bounce. What does a cubic function look like? It looks like it's got a pause in the middle. So it still cuts through, but it's a pause. 4th powers look more and more like 2 powers, and 5th powers look more and more like 3 powers. So this works for 2, this also works for 4, and for anything past it. This looks like 3, it also looks like 5, and anything past it. So it can give us some real insight into what this thing is supposed to look like, and to make us give a much better guess to say, oh yeah, this should have a little bit of a rounding on it, where it's going to definitely pause and come back up, and give me a really good, accurate picture. So if I wanted to make the most accurate picture possible, let's finish on 44. I'm going to redo it, following the rule we just discussed, and now making sure to get all the pieces right. So we have at negative 3 an x-intercept, 1, 2, 3. We have at positive 1 an x-intercept. We have at negative 9 an y-intercept. Okay, at here we have end behavior, end behavior. Okay, now this has a multiplicity of 2. We then come down, come back up, hit that. As we get up towards 1, it's going to do a cubic. Cubics, remember, level off ever so slightly, and then coming back up. And that's exactly what this function looks like if we zoom out a little bit. Like, that's pretty dang good. Like, it ain't perfect, but it's better than what we have with nothing. And so when you talk about these kinds of functions, this is what you're going for. You're looking to get as close to an accurate picture as possible. And notice how we do it. We look at things like whether it's positive or negative. We look at things like what's the degree or the power of the function, where are the intercepts, what's the multiplicity, what's the end behavior, and then we graph it using that information. The intercepts are the easiest to graph, but usually the hardest to find. The end behavior is easy to graph because it's just looking at the chart. Multiplicity can have some nuance to it, depending on what the multiplicity is, but it will always follow some general trends. Powers of 1 will simply go through, powers of 2 will bounce, powers of 3 will give this little sloop, and powers of 4 and 5 will just follow the same pattern. So in this picture, here's the axis, here's the axis. So you can see how it's just going to follow these general rules every time. Not the easiest to explain, but there it is. So let's now look at 46. Turn this off. Oop. Okay. Let's look now at, 46. Okay. So 46 is our first time seeing something a little different. So let's go through it. All right. Positive or negative? Okay. Positive or negative? Over 46, I have x, I have x, I have negative 2x. So x times x times x will give me 3x's. So this tells me it'll have a degree of 3. However, over here, we have a negative 2. That negative 2 indicates that we're supposed to have a negative power, or a negative for the function. Because we have a negative times a positive times a positive, negative times a positive times a positive would be a negative function. So if I want to look ahead, like I can already answer the question of end behavior, because I have an odd function that's negative, so I know it's going to look something like this. And so I can already come in here and say, yep, it's going to start high on the left and end low on the right. Like I can already do that because I know these two pieces. So next, I ask questions about intercepts. So let's go through them one at a time. The 3 x-intercepts are pretty easy. We have intercepts of 0, 1, and negative 3. We have y-intercepts of, let's see, plug in 0 for everything, should be 0. Again, I'm just using the pieces from last time to do that, so make sure you know that. D, the all multiplicity 1. And the last piece is end behavior, which I already have graphed. So let's take a look. Next thing I'm going to graph is these intercepts. So I have 0 on the x, 1 on the x, and negative 3 on the x. Okay? Now, look what each one does. They're all multiplicity 1, so they're all going to cut through. And now it's just a question of, if I start here, if I want to cut through that negative 3, I just have to go down through negative 3. I can't come over here and cut back, because then I'd have another intercept over here. I have to start here and go down and go through this graphing point right here. Now, what's next going to happen? Well, I have to come back and hit this point. So I'm going to have to turn around, start coming back. Am I going to hit it and keep going, or am I going to hit it and bounce? Well, it's multiplicity 1, so I'm going to hit it and keep going. Boop. Now I got to come back around and hit this one. Again, do I hit it and keep going, or do I hit it and bounce? It's multiplicity 1, so I hit it and keep going. And eventually, it's going to end up down there. And again, this process will never, ever be perfect. But it's decent. And that's the big detail. And if I graph this function, just like I did the previous functions, let's see, negative 2x, x minus 1, x plus 3, negative 2x, x minus 1, x plus 3. I mean, look at that. That ain't bad, guys. That's pretty good. Like, you'd be hard pressed to come up with a better graph without doing much more for work. And so this is the idea behind it. It's not meant to give you some massive, total mind-blowing experience of I got a perfect graph. The idea was to see, how in general does it move? How does it act? What does it look like? So These are the first three parts of your homework, which have you dealing with how do you graph the function. Notice the pieces we use are all listed out here. You need to know whether it's going to be a positive or negative, and the coefficients can tell you that. You need to know the degree, which the powers can tell you that. You need to know the intercepts, which you can find manually with the material from last time. The multiplicity, same thing. And the end behavior, which you can find from, again, 2 times ago. So, the last piece to put all that into a graph, you do the intercepts typically first, because those are the easiest things to graph. Then the end behavior next, using the grid that we just saw. And then multiplicity will tell you how to go from the end behavior to the intercepts. Remember, the intercepts are the only intercepts. It cannot hit anywhere besides that spot. And so if you're like, oh, maybe it comes over and cuts over here somewhere. No, it can't come over here because there's only 3 intercepts. We found them. If it was going over here, there'd have to be another intercept in order for it to go over there. And I can't like go around the axis because the axis, remember, goes on forever. That's why it's got the arrow. Okay. Using this same information, we can work backwards as well. This is what the second part of the homework is. And these, I always think are fun because I always think of them as like riddles. So let's look now. I think it did it again. At 48. Okay, the instruction state. For the following exercises, use the graphs to write the formula for the polynomial function of least degree. Okay, so for these ones, I'm going to go kind of in the opposite order, but I'm also going to use this exact same list. Okay, the intercepts tell me where I'm going to have my functional pieces. The end behavior is going to tell me whether it's going to be positive or negative. And then the multiplicity is going to tell me, what kind of degree we're dealing with here. So, looking at this graph, the first thing I can observe is if I look at the graph as an overall picture, it seems to fit into this top right category. It's an odd function with a x bigger than 0. Notice the bottom left-hand side goes down, the top right-hand side goes up, just like it does in the picture itself. Down and to the left, up and to the right. So I know it's going to have some properties similar to this one. Now the question then becomes, okay, well, what are those properties? Well, we have x-intercepts at -2, +1, and +3. We also have a y-intercept at 3. So let's start with the easy stuff. So first of all, the x equals -2. This tells me I have x plus 2 in my graph. The x equals 1, that tells me I have x minus 1 in my graph. X is +3, then you have x minus 3. Notice how each of these numbers is put into my function right here. So there's the 2, there's the 1, and there's the 3. Okay? Now, next thing I'm going to ask myself, so part 1, I want to go ahead and use the intercept, specifically the x-intercept, to get my first piece, which is all these little pieces. Next thing I want to do is multiplicity. How many of each of these pieces are there? Well, if I look at these pieces, let's go through them one at a time. So this first one, notice it looks like if I zoom in just around that little spot, this right here just looks like a line, which means it has a multiplicity of 1. Over here, just in this little spot, it looks like it's a line. So again, it has a multiplicity of 1. And over here, it looks like it has a line, multiplicity 1. So this tells me basically what this function should kind of look like. Next piece, want to do the multiplicity. I then want to do the last intercept, which is the y. Because it is possible there is a number out front here. That number I'm going to call A. It is possible there is a number out front. Now, I know something about this number. Because of the end behavior, I know a is going to end up being positive because it looks like an odd function, which it is an odd function, and that odd function has to have k going up. So it's going to go up over time. Well, let's see what happens. I'm going to plug in the y-intercept now. Now the y-intercept here is 3. That means the y value is 3. When the y value is 3, if it's the y-intercept, remember it's 0, 3. Which tells me that the x value is 0, meaning everywhere there's an x, I should have a 0. And I can simplify this. So once you plug this in, then you need to solve. So these first two are really straightforward. You find the intercepts and put them into the function. You use the multiplicity to fix the function. Now you need to get the a. So I got 3. With 3, a times 2 times negative 1 times negative 3. Okay, negative 1 times negative 3, this is going to be a positive 3, times 2 is 6, so I have 3 equals 6a. Divide both sides by 6, 3 over 6 equals a, or a equals 1/2. So, on 48, it asks to find the formula. This is the first piece of the formula, but it's not the final formula. The final formula is to put in a. 1/2 x plus 2, x minus 1, x minus 3. Now this piece I'm going to put in my notes here. But before I do that, I am actually going to spend some time to check my result. So, this is what I want it to look like. Let's see if that actually matches. So I'm going to pull this a little to the side. Okay, let's pull up my other window. There we go. Okay, what I get here, I got 1/2. So 1/2 times x plus 2 times x minus 1 times x minus 3. Now, I want you guys to take a look for a second. At these two. Look at that. You cannot ask for much better than that. I mean, that is beautiful. Like, you can clearly see in this one. Look at it. You've got the negative 2, 0, just like we have in our picture here. You have the 1, 0, just like we have in our picture here. You have the 3, 0, which we have in our picture here. Even because of that a, we even have these other places. Like right here, looks like it's near 2, and it's near 2. And there it looks like it's very, very near 2. And very, very near 2. Like, it would be hard guessed. We have an upper intercept of 3, just like we're supposed to based upon this picture. And we have a top number of near 4. And this one is also near 4. So that's, like, this is amazing what we've managed to accomplish with just some basic information. And that's kind of the point. Our goal is to be able to take the information we are given, which was this original graph, remember, and graph it in such a way that we're actually able to find what the equation should look like, which is damn impressive. Like, it's just impressive. Notice the process by which we did this. So if we're going in reverse, so if we are given the graph, here's our steps. Step 1, look at the intercepts. And write them out. List them out, okay? And notice how the sign's going to change. So the negative 2 became a positive 2. The positive 1 became a negative 1. The positive 3 became a negative 3. Step 2, once you get that piece down, look at multiplicity. So A, B, let's call it C. So then look at the multiplicity. How many, what's the a look like? Is it a power of 2 or a power of 1? Is it a power of 3? What do we know? Use your context clues to help you with this. It's always possible that they've given you everything you need. You just need to look for it. If it looks like it's going through and it's aligned, then it's going to be a power of 1. If it looks like it's going through and it's, bouncing, then that's a power of 2 or possibly even a power of 4, but usually a power of 2. And in here, a power of 3. And then the last step is going to be to look at the y-intercept. And use that to find that number out front, which in my example we called x, but to be consistent, I'm going to call it k. To a power x minus b to a power x minus c, and solve for k. That's the big thing. This is how we're going to do this process. And now we're going to do the exact same thing, but using it with number 50. So I'm going to leave it up here so you can kind of see it. Right there. All right, 50. So on number 50, here we go. So same basic process. Okay. On 50. So step 1. Intercepts. So specifically the x-intercepts. I'm going to write them out. And my x-intercepts for this one are -1 and +2. And how I'm going to write them out is x plus 1 and x minus 2. Flipping the signs. Now, part 2. What about multiplicity? Okay. Well, if I look at the -1, look right here. Notice how it bounces. Bounces, remember, are multiplicity 2 or 4. We're going to assume it's the lower number to make the math easier. It's always possible that it could be a higher number, but you'll notice a phrase in here. It says of least degree. It's always possible it could be higher. We're not concerned with that. We just want the smallest one. So what this tells me is that x plus 1 is actually squared, whereas the x minus 2 is actually by itself. Because notice the 2, it goes straight through the 2. No subtle stops. It just goes straight through 2 like a line. And so it's just a power of 1. Whereas the -1, it bounces, which makes it have a power of 2. This is looking good so far. Okay, now 3. Now I want to do the y-intercept. Now the y-intercept in this case is at 0, 2. So I'm going to throw that letter out front. I'm going to call k. My pen is dying. Go a different pen. So plus 1 squared x minus 2. Okay, so what I'm going to do now is I'm going to take 0 and 2 and plug them in. So this is the equation that I have so far right here. I'm going to plug in 0, I'm going to plug in 2 for x and for y respectively, and let me use that to find out what k is. So my y should be 2, k is just k, my x is 0, my x is 0. Okay, let's figure this out. So 2 equals k. 0 plus 1 is 1. Square that is 1. 0 minus 2 is -2 to the first power. Why am I writing a 2 there? I don't know. To the first power is going to be -2. K times 1 times -2 is going to be -2k. And I can divide to get k by itself. So I would get 2 over -2 equals k, or k equals -1. I can now write my final solution, which is to take this top equation and plug in k. So let's do that. Take the top equation. Y equals -1 x plus 1 squared times k x minus 2. I'm going to leave the 1 off because this is important. And in theory, this should look like the exact same graph. Let's test that theory, shall we? So once again, I'm going to pull this over. Turn this on. Okay. Let's graph this function and compare them. So negative 1 times x plus 1 squared times x minus 2. Oh, look at that. Like, sorry. Oh, look at that. That is freaking beautiful. How could you expect to get any better than that? Those things are just perfect. Everything matches, right? You've got the negative 1 and the negative 1. You've got the 2 and you got the 2. You even got this 1, 4 up here and this 1, 4 up here. And the 2, 0 here and the 2, 0 here. Like, that's amazing. And when people always ask, why graphing is so difficult, it's really not, but it's a process. And it's a process where you have to know all this information over here in order to get it to work out. Like, you have to know all of this stuff in order to graph a function like this. Whereas by comparison, like solving an equation, you just need to kind of know the basics. But to graph it, you got to know so much more. And even skill, like, think back to what our graphs looked like before. Like, they were by no means perfect. Like, they would barely pass the test to say, yeah, they look similar. But, they're still better than not having any graph at all. And so this is incredible, like what you can do with this information and how you can use it to find different solutions. Okay. Do one more of these. This is number 52. Yep. Okay. This one, I'm going to go a little faster. All right, I'm going to use all the same information I had before. But now I'm going to showcase kind of what this looks like when it's unleashed. You ready? All right, step 1, intercepts. I have intercepts of negative 3, negative 2, 3, and 4. That's my full list. So what's that mean? I have x plus 3, x plus 2, x minus 3, x minus 4. They're my pieces, okay? Powers. So we did the intercepts with respect to x. Now we do the multiplicity. Okay, none of these have any fancy things going on. They're all just kind of going straight through. So straight through, yeah, it curves up here, but we don't care about that. We care what's happening at negative 3. And at negative 3, it's just going through. It's not pausing. It's not bouncing. It's going through. So this tells me the 3 has the power of 1. The 2 has the power of 1. The 3 has the power of 1. The 4 has the power of 1. They're all powers of 1 here. Okay? So multiplicity is now taken care of. And so now we need to take care of the y-intercept. So we should have y equals k x plus 3, x plus 2, x minus 3, x minus 4. And the y-intercept for this problem is at negative 3. So we do negative 3, k, 0 plus 3, 0 plus 2, 0 minus 3, 0 minus 4. All right, negative 3 equals, all right, 0 plus 3 is 3, 0 plus 2 is 2, 0 minus 3 is negative 3, 0 minus 4 is negative 4. All right, one piece at a time. 3 times 2 is 6. Negative 3 times negative 4 is positive 12. So k times 6 times 12, that's 72. So you have negative 3 equals 72k. Divide this by 72. So you get negative 3 over 72 equals k, or k equals negative 1 over 24. That tells me my final solution should be this original equation written with k in it. Y equals negative 1 over 24 times x plus 3 times x plus 2 times x minus 3 times x minus 4. And just like before, I'm going to attempt to graph this thing. Okay, negative 1 over 24 times x plus 3 times x plus 2. Okay, times x minus 3 times x minus 4. Look at that. It's just beautiful. So there you have it. Now, the last pieces of your homework all deal with the same basic process, but instead of giving it to you in picture form, they've given it to you in word form. Now, it is my opinion that these ones down here are actually easier because they've given you all the information. You don't have to look for it in the picture. The difference is you have a little bit harder time because you can't compare it to the answer. You can't just come in and be like, let me just graph them and see if they match. Like, you can do that on all the other ones, but you can't really do it on this one. And so these ones, they've taken all this same information and kind of just listed it out for you. So they list, it has these roots, it has these multiplicities, it has these intercepts. Like, it's very helpful to have problems like 57 and 59. And if I need to, next time I will start by doing one of these problems. But I'm kind of running at the 50-minute mark, and I know that's a lot of information to take in. So I will go ahead and stop it right here. This is a good place to let off. Let's go ahead and take a look back at our notes. So there are two big parts to our notes. How to do it when you have to graph it. Notice there's two parts. The information you need to find is over here. How to actually graph it is right here, including with the multiplicity, what to do. If you're looking at the graph, how to work backwards to find the equation is by these three steps. It looks short because there's a lot of information contained here. And so use the examples here. And the textbook does have examples on the previous pages if you need extra examples worked through. So please use the information we have so we can find this information and get this thing done. That'll be it for me today. Make sure to note your homework assignment tonight. 5.3 part 2, 43 through 63 odds, same pages as before. I will post all that in the description, and I'll see you guys on Thursday. Have a good rest of the week. Okay.